Hey everyone, I'm Surendra Anubolu, working for Broadcom. I'll be presenting with Dr. Nikhil Shetty from Oracle and OCI. Thanks for the opportunity. OCP is a great forum. In-network compute collective is technology that we have been working on, and today we'll go over the details. I'm hoping to get support from you. Any questions, you can take it here right after this. Okay, so today we'll go through some sequence. I think we'll plan to go over bandwidth and latency needs for AI fabric, and then what are the challenges, what is happening there, and why we need it. And then there's a proposal for like how you could do in network collectives. Then follow that with, we'll share some data. And there's like a slide that we have Tomahawk Ultra device that is announced, and it is working very well. And then we have some data from the actual real hardware that shows how the acceleration happens and how much performance advantage we're getting. Nikhil will go over the OCI related use cases, and then go over the call to action and the software part of the INC. Okay, so the first one is, I want to go over AI fabric, what are the challenges? I think many of you are probably already aware, but I just want to give you some, I've been saying in network collectives, what is a collective? Collective is basically you have a distributed either training, a distributed inference, and all these multiple nodes, multiple GPUs are working together. They're collectively working together in exchanging the data, and that is the collective. So there are many types of collectives like this. Initially it came up from MPI, then went over to CCLs like Nikhil, and other Bickle, Hickel, with many CCLs, XCCLs. It went over there, and there are few collectives that are very popular, and I listed 4 of them here. But basically a collective is a group of nodes, in this case GPUs, that are sharing the data, and it's mostly communication dominated. Okay, so the collectives doesn't necessarily mean there's a computation. Some other collectives have computation, like AllReduce and ReduceScatter have computation. All2All and AllGather do not have any computation. Okay, so why is this a big deal? Is because if you look at the communication between the GPUs, most of the communication happens is using collectives. There is peer-to-peer transfers that is very, very little. I'll show you a slide right after this, but most of that happens with the collectives. And with the model sizes growing and also the performance needs that are going up, you have large amount of data that's exchanged very, very frequently, so which drives very high bandwidth. So there are 2 different aspects of this. For training, the throughput is very important, and for inference, the latency is very, very important. Right? It's like when you are typing a query, you want to see the tokens per second. That's very important for the single user. And for training, of course, you have batch size, and the throughput needs to be high. And there's one more thing that actually I want to highlight here is the mixture of experts. Mixture of experts have been around for a while, but has become very, very popular with the recent, actually early this year that DeepSeek has published a paper, but mixture experts was in news even before that. It introduces what is called K of N multicast, where you may have 128 or 256 experts, and only a subset of them will be getting the token data. So, and that is actually very, it's like a blocking communication. There's basically that can hold up, that can make your GPUs idle. And even accelerating that would give you good performance improvement. Okay, so now that I have what is a collective and what is the bandwidths that we're talking about, so I have taken from one of the papers that says, okay, that profiles, and we also have profiled on the, when we run some other training inference to see what's happening, where the bandwidth goes. So depending on the type of parallelism that you do, usually for any training or inference, you do multiple types of parallelisms that's active. So long time ago, it started with the data parallel, which is already used, right? So that is still, the fabric load is not as much, but as you get into very large models, then you are splitting the tensors across. Tensor parallelism actually results in AllReduce. If you think of tensors, these are large matrices, and when you multiply matrices row times column, you can think of it as if each GPU is doing a portion of the tensor, eventually somebody has to add them up together, and that becomes like a reduction operation as well. Right? It's like, and then there's expert parallel. We just talked about k of n and other types of gather activities that you want to do. So all these parallelization activities take the fabric load. And if you sum all of them up, there is huge amount of collective bandwidth that's going on. And peer-to-peer, which is a pipeline parallel uses, is actually pretty little. P2P does not use collective, but it's like that amount of bandwidth is very little. So the point I'm making here is like large amount of bandwidth is going towards collectives, and accelerating that is very useful. I have not had that slide, but actually there is amount of exposed, means like this computation and communication overlap. So even if you speed up the communication, sometimes you may not see as much effect, but there's a lot of exposed, means there are times where GPU is idling for the collective to finish. And that amount of time can be 20% or 30% or 15%, depending on the type of the model you're running. Like GPT OSS is doing well, and if you go profile it, you'll see how much communication is going on, and that may have 10 plus, like about 20% of the bandwidth that it's waiting on when you're doing the inference. Okay. So this is an example. So hopefully I made the case on like why collective acceleration is important and why offload it. Like GPUs are so powerful, they're so big. How can a network do anything to support that, right? It's like the key idea is this: GPUs are compute heavy. Like even as like recent GPUs, if you take it, 1 petaflops. But pretty much everybody is able to do it. Like the 1,000 teraflops is not out of the ordinary. So, but amount of network bandwidth they may have a scale-out bandwidth of 400 gig to 800 gig, and scale-up bandwidth of few terabits to maybe 10 terabits as well. So, but that's still very small compared to the flops they have, right? And then if you look at the switches have huge amount of bandwidth. They have like 50 terabits per second, or even 100 terabits per second. But right now they have, prior to Tomahawk Ultra, they had like 0 amount of computation capabilities, right? So now if you look at the collectives actually do not need as much computation. They so even if you're trying to do something wire rate, let's say think about a very simple equation. You take 50 terabits per second. If you're sending 16-bit numbers, 50 terabits divided by 16 is only 3 teraflops. So if you can add 3 teraflops of computation, you can do wire rate collective acceleration. Okay, so the idea is that, okay, we want to do that. We want to do, by doing this costs very little but gives you a huge improvement. That is the right place to do. So because GPU is so heavy but very little network. So, okay, so Fabric is the natural place to do because it has huge amount of bandwidth. Okay. So if you're convinced that, okay, Fabric is the right place to do it, then how would you go about doing that, right? It's like, so there's one of the ways that of doing this is a hierarchical methods which scale very well for the scale up and scale out. Like the hierarchical methods scale very well whenever you have more than one layer of the networking, where the amount of data goes up, will reduce over time at each level. Nikhil has a slide that shows that. So offload, so basically the switch is participating in the collectives, and the switch is the endpoint for you. Like the GPUs talk to the switch for the offload, and there is a software that gets involved. There is another session in the afternoon by Vlad and Mahesh at 3 o'clock or 3:15. I encourage you to attend that for how the INC manager and the software plugins work on this to make this very, very transparent. And then there are plugins that are developed. One is INC manager, is one software component, and there's a XCCL, which can be Nikhil, or whatever other CCLs, libfabric and MPI plugins can be developed, and some of them are available. And then they can make the work very transparent. It's basically anything on the higher level doesn't need to know that this offloads are happening, because the CCL plugin or the libfabric plugin or the MPI plugin can actually can hide all of that for you. Okay, so and then okay. So now that, okay, we talked about, okay, INC manager that sets up a tree for you, and then switch is participating and able to do this, then I want to talk about very specifically about INC in the switch silicon. I'm showing this just to say that it is feasible and it's doable, and to encourage others to do the same, and also work together to say that, okay, work together to make this ecosystem more diverse. Okay, so Tomahawk Ultra that was supports INC in the pipeline. It's wide rate, and it supports two methods of doing in-network collectives. So why two different methods? So there's inferencing, there's training. They have kind of different requirements. So one of the method is like uses reads. It's called pull method, where the switch is the center of it. It can actually read the data and take care of everything without much of the GPU involvement. It's able to read the GPU memory and do the computations and write the data back, so that it's very transparent to the GPU. And then there's a push method where it's the GPU actually pushes the data and the results come back to the GPU. So one, like a pull-based method is very scalable, and push-based method is actually very, very low. It offers you better latency. So both are supported in the Tomahawk Ultra. And the way it works is Broadcom believes in standardization a lot, open ecosystems. And Tomahawk Ultra can work with any NIC that can support standard RDMA. So there's no proprietary headers. It's a standard RDMA headers, as long as you can support. Let's say if you can support RDMA writes, then okay, you can work with the push. And if you can support RDMA read, it can work with the pull method. If you support both of them work. So there's no specific requirement on the NIC itself, as long as it supports RDMA. Okay. So, and then as we go on, I have one more slide that to go over. So this one is early lab data that shows how the collective acceleration, what the data that we collected. And we have a testbed that that's running with 60 nodes here. There's the data that's shared. We have testbed with up to 64 nodes. And I'm showing a part of the data. Actually, the data scales pretty well up to 1 gigabyte. I don't mind sharing it. Just that in the scale of things, because it's a logarithmically going up, the chart may not look as nice, but I think there's data all the way to 1 gigabyte that shows the reduction in the time. So what we see is that there are two things. One is you see collective performance improvement by 2x, and you also see much more predictable latency. Why is there more predictable latency? Because if you are looking at regular ring-based protocols or other ways of doing this, or like a broadcast-based protocols, there's always a chance of incast and other things that happen. There's a congestion that happens. Here, because switch is wire rate, it's much more predictable. As long as only the variability that here is when the data is being pushed, there may be variability in terms of the HBM bandwidth, so there may be some variability. But from network point of view, there's no variability, because once the data comes in, everything is moving at wire speed. So there's no variability there. That gives you much more lower variation from run to run. And the performance scales very well with the number of nodes. We are testing with 64 nodes, but like we have done simulations with much larger. Because it's a hierarchical, you can, at least technically, there's no limit on the number of nodes it can you can support, because everything happens at like 1 tier, 2 tier, 3 tier. It'll go through. The other thing that maybe I can note here is that the data is pretty replicable in the sense that if you run INC multiple times, like if you run the same collector multiple times, you can reproduce it. That makes it, the debug is easier. Like we heard like from some other customer that, okay, reproducibility is important for debugging and maintenance there. And I think, so basically the bottom line I'm saying is here is that the performance, this is tested with OSU, but we also started to run with CCLs. I will have the data pretty soon on the CCLs as well. I expect that with CCLs, it may not be 2x, it may be more like maybe 30, 40, 50%. We're there to see. That's because CCLs optimize chunking and everything very, very well. They do a good job. So they have chunking and channelization and the methods. So compared to what happens in the OSU test, but still I'm expecting significant improvement in the performance there. And I'll pass it on to Nikhil for OCI.
Thank you. My first, on the slide, the first line was to introduce myself, like, hey, what is OCI? We're building 100K clusters. That's why we're like interested in all of this. But I think, you can see I put August 2025 there, and by now I guess everybody would have seen all the press releases. So all these numbers are, we are going way beyond this right now. So I think there was a release like just this week, which is like 800K GPUs. So take it with a pinch of salt, at least the slide. So, what are the problems that we face here at OCI, right? Like you can argue, hey, all of these collectives are running on the endpoints. You're selling bare metal to these clusters. Why do you care? Like, why do you care what we do? The reason why we care is the data that traverses these switches, as part of the collective, they have to traverse multiple times. So as a simple example, like in all reduce, if you do a collective, you're sending 2 times the amount of data onto the network. Okay. As part of optimizing our performance for all our customers, we actually have some kind of intelligent, collective aware load balancing and stuff like that in our fabric. So we already have a pathway where we are saying, hey, in our fabric, we are going to do something that's collectives aware, right? And we're going to load balance flows and things like that in a way that we get the best performance. So that's already in place. So kind of offloading collectives is not new in that sense, if you look at it, right? Like we're already trying to do that. So what are the benefits that we as OCI see for in-network collectives? It definitely minimizes higher layer congestion. I mentioned like half the amount of traffic, so that's immediately a win. The data traverses only once, right? It goes up the tree. You're going to go, as you go up the tree, you're going to do the reduction if required, right? All reduce and things like that. Where it's not required, it's just it's just kind of like multicast in some ways. And then the results will come back from the root of the tree. So again, just once, you just kind of like a multicast tree, it's being sent to all the endpoints. So Surendra showed us like it dramatically lowers the completion time for collectives, right? It improves the tail latency for our customer workloads. It also frees up compute, right? Like because instead of the GPUs doing all of these calculations for the collectives, they can they are freed up to do other computation that they want to do. The last one is the key point for us, which is if we do this for one of our customers, if our customer adopts this, we actually free up bandwidth for other customers, or maybe even the same customer has multiple jobs. It opens up the bandwidth for the other customer. So there's a lot of benefit of offloading collectives into the fabric. We are on the last slide. So this is the call to action. But just before that, I just want to close on what our point of view is in terms of in-network collectives. We want open programmable interfaces, right? We want to be able to configure and monitor these in-network collectives in an open way, right? We need secure multi-tenant partitioning. We want to make sure like this is data, the customer data that's sitting and you're doing something with that, transforming that. You want to make sure that it gets wiped if we are handing one switch to some other customer, right? Like for different collective. So we want to make sure that is in place. We need this for both scale-out and scale-up fabrics. I would say this for scale-up fabrics, it's very critical. And then for scale-out, we can have it as a secondary thing. But I think scale-up, it's really critical to have this feature. And then in terms of where we come with respect to OCP, with the SAI switch abstraction interface, we have an ability here. We have an open interface that we could use to configure INC in hardware, right? And also collect the telemetry. So we definitely want to contribute to that effort in OCP. So I think that's what I wanted to say here. Thank you so much.
Thank you, Surendra and Nikhil. Any questions? Yeah, me already.
Yeah, hi. I hope I'm asking the right questions here, but regarding in-network matrix computations and cut-through switching, could you help us understand that a little better? Is it store and forward? Is it cut-through when you're doing in-network computation?
Okay, so there are two different things. There's an in-network computation that's going on, and at the same time, you can have some other traffic that's going on. So in-network computation itself, the switch is the endpoint. That means it is not even store and forward. The traffic gets terminated. So there's an RDMA transaction between the GPU and the switch initiates a new RDMA transaction. So cut-through does not apply here.
So would you say it's buffered?
This is the endpoint. So yeah, the packets come in for anything that requires in-network computation. They get buffered and then computed and sent back. Yeah.
in terms of aligning the matrices between, the incoming neighbors, in order to minimize your buffering, how do you coordinate the reception of matrices from your neighbors so you don't overbuffer?
Yeah. So there are two protocols that I talked about. One is a read-based protocol. The other one is a write-based protocol. It can also be called pull versus push. In the pull protocol, the switch has a lot of autonomy in actually initiating the read transactions from each of the GPU memories, and it's going to initiate from, it can do parallel requests actually. So it can say, okay, hey, let's say there are 16 GPUs that are involved. All the 16 GPUs, okay, give me this one segment of the data. And then when it's done, then ask for the next segment of data. And whereas on the push protocol, it is coordinated through the switch create control and also through the CCL plugin or the MPI or libfabric plugin. So if the MPI and libfabric plugin, they do it at a course level, and the switch does it at the final level through congestion control.
Okay, and you mentioned there's no additional protocols involved, it's just Rocky coordinating flow.
Yes.
Okay.
So let me clarify that to you is that the data plane is pure Rocky. It can work with any NIC, but there is the plugin that's involved that we plan to contribute that will send, has the control plane message that says, okay, now these are capable or not capable, and there's a more detailed talk in the afternoon on the INC manager.
Okay, but there's no additional protocols involved.
There's
it's just UEC and Rocky. Yeah.
Yes, okay. Everything is a standard Rocky. Any NIC should be able to work.
Okay, thank you.
Okay, we have only 4 more minutes left, so please keep your questions small and not have too many follow-ups. Thank you.
Sure. Hi, this is Aditya from Cerebrus. One question and one comment. The comment is also consider that there are architectures that don't have scale-up fabric, so I think this is also important for scale-outs. And the question is about, since the in-network collectives map pretty closely to multicast topologies, have you also considered using like offloading the tree distributions to the network using like beer or any kind of multicast architectures that will also offload the collectives to the network?
There's discussions on that, but currently what we are planning to release, the INC manager, which is the after talk, it's based on the controller base, and that's initially done because that gives a lot more control. Like we don't want the tree to be changing, which requires other additional configuration as well. But your comment is valid, actually. That's being considered as well.
Yeah, thanks.
Great talk. The question is about INC in the scale-out network. In the past talks, earlier talks, people are talking about using adaptive routing, packet spraying in the scale-out network.
Yes.
How would that work with INC?
Yeah, so the key thing to remember is, in this case, the switch is the endpoint. So even if there's a spraying going on, by the time it reaches the switch that is doing the INC, they all converge there because the packets will have destination IP address of the switch. So they will reach there. So it's not that the switch is snooping the data. Okay. Switch is the endpoint, so it will get all of the data. Switch will see all the data, whichever is doing the INC offload.
Okay. So the adaptive routing path is constrained towards the root switch. It's not. It cannot use all the routes. I cannot choose multiple spines.
No, there's a standard routing protocols work, but eventually because the IP address is a switch IP address, they will whatever is requiring the service of that switch will converge there.
Okay. Yeah.
Thank you. Can you please take that offline? Thanks. Last question, please.
Yeah, thank you for the interesting talk. I was wondering if you can quantify the performance improvement in collectives with this approach.
Yeah, I have a slide. I think probably the slides will be posted sometime.
In a week or two.
In a week or so, you will see the data. And if you need, I'm not sure who you are from, like, you could message me. I don't mind sharing with you. But I think if you wait a week, you will get the slide with the performance data.
But theoretically, it could be, half.
It's 2x.
Half, yeah, 2x.
So right now, it's a 2x and 2x plus is what you see in the, it's not theoretical, actually, it's the measurement data. And it's a 2x.
But in reality, I guess there is synchronization issues, and that may result in some overheads as well. So.
Yeah.
All right. Thank you, Surendra and Nikhil.
Okay.